So the Mobius function. I'm jumping over a section, the one on perfect numbers. We'll talk about those. We'll talk about perfect numbers later, after we are done with our exams, things like this, our homework, our exams, because they will not play a role. In fact, there are open questions on perfect numbers. Probably the oldest unsolved problem in entire mathematics. The oldest, say, unsolved problem that was recorded in writing, so to speak, from ancient Greeks. It's still unsolved. Like those three problems with trisect the angle and duplicate the cube and square the circle, those were solved. That constructions are not possible. There's a problem on actually several, on perfect numbers that are still unsolved. Like, is there any odd perfect numbers? All the perfect numbers found so far are even. We don't know. We'll talk more about those, but after we're done with the more important, more important topics. So I jump over this section. It's not part of our exams, but we'll talk about the Mobius function. The Mobius function, however, it's so difficult to work with in general that it forces us, when we test ourselves with problems on homework or exams, to make them easy. There are so many unsolved problems on the Mobius function. Even the Riemann hypothesis, because we were talking about that, that has $1 million prize on it, can be restated in terms of the Mobius function. So, but we'll talk about all those things later. All we need about the Mobius function is how to compute it, what it means, definition, how we compute Mobius function. So the quick properties. So go like this. That would be section 3.6 in the definition. Is we use this notation, another Greek letter. Say n, mu of n, if you want mu from Mobius. So Mobius is a name, and this is a Greek letter. Is 1 is defined by definition. Is 1 is f. So this is another arithmetic function. It's defined only for positive integer numbers n, and if n is 1, it's just defined to be 1. It's defined to be 0 if n is not square free. What does this mean? If n has at least one prime factor that appears with an exponent that's strictly larger than 1. So let's see how we write this. If there is a prime p such that p squared divides n. So if p squared divides n for some prime p, and the remaining case is when there is no square of a prime that's a divisor of the number. So if I think about the prime factorization of the number, it cannot have any exponents larger than 1, because then the Mobius function will be 0 by this second condition. So then the number will simply be a product of distinct primes, each one appearing with exponent exactly 1. And if that's the case, so if n is a product of different primes, say p1, p2, I don't know how many, say k of them, pk, say with p1, comma, p2, comma, pk, distinct prime numbers. Distinct primes. Then it's defined to be -1, to the k, where k is the number of such primes. So this looks complicated, and it is. The good news is that we don't need to know anything else. There are some things known, which are about the Möbius function, but not as much as we would like. Okay, so we just use definition. Although it does have the same properties, not the same properties, it has this same property as the others before. This is a multiplicative function. And one can check this immediately. So I write this as a theorem, if I have it here. If I don't, I think we have this. So this, from our point of view, this section will be very simple, very quick and simple, because there isn't much we can do about this function. So the theorem is, I guess, 3.13, if I'm not wrong. Möbius, the letter on his name has this. The Möbius function is multiplicative. And again, it's not completely multiplicative, like the others. It is not. Completely multiplicative. And to see any example we want of, say, mu of 6 times mu of 6 is not equal to mu of 36. It's not equal. First of all, what is mu of 6? It's the first example where we are forced to go through the definition and understand the definition. 6, I'm not in this case, n is not 1. I'm not in this second case. There's no prime number whose square is a divisor of 6. 2 is a divisor of 6, but not 2 squared. So I'm in the third case. Now in the third case, n is a product of distinct primes, and 6 is a product of distinct primes, 2 times 3. What do they say here? I look at how many primes I have, k primes. K is 2 in my case, I have 2 primes. So the Möbius function is minus 1 to the k is minus 1 squared in this case. So Möbius function of 6 is minus 1 squared because I have 2 primes, and that's plus 1. So the Möbius function mu of 6 is 1, mu of 6 is 1, but mu of 36 is not 1, is 0. Because 36 is a multiple of 4. So 2 squared divides 36. 36, it's already 0 because of this reason. I was going to say that 36 also is a multiple of 9. So for that other reason, so they're not equal. Okay. A nice theorem, and actually important in number theory, is the so-called Möbius inversion theorem or Möbius inversion formula. We will not use, but I'll mention this. Okay, I think I'm going to write again definition. So we have it. Mu of n is 1. Is it too high? No. 1 if n is 1, 0, if there is at least one prime, p squared divides n, that's such that p squared divides n for some prime p. And the third case is when no square appears in the prime factorization. The number then is forced to be a product of distinct primes, p1, p2, say pk, and in this case the Mobius function is minus 1 to the k. Mobius inversion formula will not play a role in our case, play a role in the homework. I don't even know if it's this homework or the next homework, whatever homework it is. It doesn't matter. First of all, what I mentioned, but first of all, I wanted to compute some values. So we get a feel for what's going on and how we compute it quickly. I'm going to make a table, quick table. Let's say compute numbers, the Mobius function for all numbers up to 20. 1, 2, 3, so to see how quickly we can compute. 3, 4, 5, 6, 7, 8, 9. No, this is totally wrong. Sorry. How can I put 20 numbers? 15. All right. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay. Mu of 1 is 1 by definition. Mu of 2 is minus 1. No square of a prime divides the number. Actually, the number is a single prime. K is 1. There's a single prime involved, so it's minus 1 to the 1. And I keep this in mind. Anytime I have a single prime, it looks like this, just P1. K is 1, nothing else. It's minus 1 to the 1 is minus 1. So, mu of 3 is minus 1. Of 5 is minus 1. Of 7 is minus 1. Of any other primes? 11 minus 1. 13, it's minus 1. 17, it's minus 1. 19. And 19 is minus 1. Then, now let's take them in order and see. 4. The Mobius function is 0 because it has a repeated factor of 2 in it. 6. The Mobius function is 1. Was computed earlier, or we see this directly. Again, it's a product of 2 primes, 2 distinct primes, so it's minus 1 squared. 8. Repeated factor of 2 in it, so it's 0. 9. Repeated factor of 3 in 9, so it's 0. It's very easy to compute concrete values. Because I'm saying if we have a problem like this with the Mobius function, it's immediate problem. Just need to remember definition. Okay, 10 plus 1, because it's 2 times 5, a product of 2 distinct primes. It's plus 1. 12, 0. So we have 2 square divisor of 12. 14, 2 times 7, so plus 1. 15, plus 1. 3 times 5. 16, mu of 16 is 0. It's a repeated factor of 2. What else? 18, it's 0 because we have a 3 square that divides. And let's say 20 as we want it, it's still 0 because I have a repeated factor of 2 in it. So it's very easy to compute them. So if I have a problem like it's good with you know. Let's say find the largest integer number less than or equal to 50 for which mu of n is 1, or for which mu of n is minus 1, or for which mu of n is 0. Let's do all 3 of them. That's the example. I would suggest we just compute them. We don't need any calculator to compute. We just compute them by using definition. So, as an example, find the largest. Why? Let me change this. Find the smallest, not the largest. See. Find the smallest n larger than 50 for which this happens. I was going to say, how do I know that I have a number less than 50? How do I know that the problem is well defined? There is a largest number, but then I realized, of course, I have a 1, I have a -1, I have a 0. We have them in the table. So it was okay. So find the largest number, m, I don't know, n doesn't matter, less than or equal to 50, such a number such that for which the Mobius function mu of m is equal to 1, say. Or let's solve also the problem with -1 or with 0. 3 different possible problems. I don't know. I don't have a criteria. I don't have I don't have any method except for trying the numbers in order. When I try the number in order, I just compute the value of the Mobius function. Unlike other functions, in this case, I cannot get the Mobius function, say, at n, if I know it at the previous value, the next value. Mobius of 49 is not going to be told us by knowing what Mobius of 50 or 51 is, or 48. They look pretty much independent from each other. So, the largest number, m less than or equal to 50, such that one of these happens, I just compute. I say we compute, that's my solution. Mobius of 50 I can do it in 2 ways. By cheating or by being honest. By cheating means I open a table. There must be tables with hundreds of thousands of values for the Mobius function, because this is an important function. And I look at it and I read and I see what it is. And I just put the answer. No, that is cheating. I'll do it in a way that, for instance, if I know that I write something that someone will read later, like a grader, someone, or a friend or someone, and I want them to understand what I'm saying, I write it like this, without much explanation. I say Mobius of 50 is Mobius of, and I put a prime factorization of 50 here. And it's 2 times 25, so 5 squared. So 2 times 5 squared. And I say this is 0 because I see the square in it. I don't have to explain. But they can see why I know that it's 0. I didn't copy from anyone. I just got it from here and the actual definition that I'm supposed to know. I don't have to repeat the definition on any homework or exam. I'm supposed to know. So, the answer to this problem, the third one, is that the answer was 50 already. 49. Let's say that's 7 squared. And that's still 0. Oh, we have 2 consecutive values that are 0. While I talk here, you can take this small problem as a small challenge for the next few minutes. Can you find 3 consecutive values that are 0? You can. And explain us what you did. So, I look at Mobius of 48. Oh, don't bother. We got it. 48. Find 4 consecutive values that are 0, if you can, please. I mean, because I see it's a multiple of 4. So, I write it as mu of, what's this? 16 times 3. 16 is 2 to the 4 times 3. I have a repeated factor of 2. So already 0. Wow, all these 3 are 0. Then I come here. I don't know. I think it's more visible here. Mu of 47. That's -1. That's a prime. We know it's a prime. K is 1. The Mobius function is -1. -1 to the k, and k is -1. So this is solved. Let's see if we can find a plus one. Next one. 46, I write it as follows. I can see it's 2 times 23, a product of two distinct primes. It's plus 1. To show a grader that I understand, y is plus 1. I write 46 inside. So before I compute the Mobius function, I write 46. I rewrite it as 2 times 23. I can see it's a product of 2 primes inside. And the Mobius function is 1 plus 1. Okay, so we found it in all these cases. While you are working, may I suggest a small hint? If we arrange a number to be divisible by 4, the next one to be divisible by 9, the next one to be divisible by 25, this is what you are doing. And use the Chinese remainder theorem, they will tell us that such numbers exist. And you can actually find it in practice. Okay, and you tell us and we check. Good. So while you do this, we talk about the Mobius inversion formula, just to state it. But this is applicable only when the situation is like that. In many problems in number theory in general, and sorts of research papers in number theory, we see it apply. But for us, we cannot. We will not do it. As you see, it involves lots of different values of the Mobius function, which we don't have to. We don't have the luxury to ask a question like this on the exam to compute lots of values. So compute a few of them. Well, let's write it anyway. The statement, it's theorem. It's 3.15. So-called Mobius inversion formula. And it says basically the formula that if I have two functions, they are related in a certain way. So let's say let f and g be arithmetic functions then if we can write n, if we can write f in terms of g in the following way, f of n is the sum over the values of g this means the sum over the values of this function, of this second function g, at the point or at the number d, that's a divisor of n, and I take the sum over all the divisors. So over all d, they divide n, positive divisor, of course, d larger than 1. If this, then the following thing happened, and if the other thing happened, then this happened. So these two are equivalent. So this, if and only if g of n is the sum of f computed at n over d instead of d. If d is a divisor f, n over d is still an integer number. It's complete. D divides n with the Mobius function, mu of d in here. And of course, and d is larger than 0. But the way they wrote it, I don't quite like it, because what it needs to say is not the following. if f of a particular value of n is written like this, then g of that particular of n is written like that. No, no, no. If this holds for all n, then this holds for all n. And if this holds for all n, then this holds for all n. So this is it for all n. If and only if this for all n. For all n. So this is the so-called Möbius inversion formula, but it's a complicated thing to use in practice, because it works when we have all these divisors. Well, we know from previous sections we can count the number of divisors, or maybe the sum of divisors, but you see, we don't know how to compute the Möbius function in here. So we have to compute it, so to speak, for every single one of them. And if the number has lots of divisors, in order to apply this in practice, it's going to take a lot of time to compute. Okay. So I will erase this and won't use it again. But I will state another theorem. They don't even write it as a theorem, but that's the one that is useful and is used in the proof of the other one. And this is the one that everybody knows. I mean, everybody who's doing number theory, working in number theory should know this. So they state it as a proposition 3.14. It's a theorem, they state it as a proposition. It's a theorem and it's a very nice one, and it shows that Möbius is a special function. It's in fact the only function that's the only arithmetic function that satisfies this property. And it says the following, that if you compute the values of the Möbius function for all the divisors of any number n you want, d divides n, the screen is black, but I hope this doesn't interfere with record. This is always equal to 1 or 0, believe it or not. It's 1, and we know when it's 1 and we know when it's 0. And it's 1 only if n is 1. So this is 1 if n is 1. And it's 0 if n is larger or equal to 2. So otherwise. So in all cases, when you take the Möbius function and you take the sum over all the divisors of a number, you get 0, except when your initial number was 1. Like if n is 1, it has only one divisor. It's 1. Mu of 1 is 1. Okay, I can see this. It's just one term. But why do we have the other? I just want to see, say, this example. Or one example that comes from here. Say, but it's very nice. It's a very nice result. It's the basic property that people use when they work in research papers, things like this. With Möbius function, this is what they use, this property. Again, we won't need it in our exams. But let's check in one case. Say n is 18. What this says is the sum over all the divisors of 18, the numbers d that divide 18, for mu of d, is 0. But let's see if it is 0. First of all, what are the divisors? 1, so Möbius of 1, Möbius of 2, another divisor, Möbius of 3, Möbius of other divisor 6, Möbius of 9, 18. Am I missing any divisor? How can I check quickly, regardless what the problem is, if I'm missing divisors? Well, how many divisors I should have? I know from a previous section. Quickly, the number of divisors of 18. Question mark. I write 18 as 2 times 9, so 2 times 3 squared. Number of divisors was the easiest of this function, this arithmetic function. Number of divisors of 18, add 1 to each exponent, multiply them. 1 plus 1 is 2, 2 plus 1 is 3, 6. The number of divisors is 6. Let me see. I got all of them. 1, 2, 3, 4, 5, 6. Yes. Well, I got the divisors, so I wrote it in this long-term or longer form or format. But it's the same thing as this sum. By definition, this symbol. It means that. But I still need to compute the values. Now, we already have the values computed. The values for the Mobius function. And let's see, this one is, mu of 1 is 1. Mu of 2 was, mu of 2 is minus 1, and I hope that it was minus 1. It's minus 1, it's minus 1. Mu of 3 is minus 1, this is minus 1. Mu of 6 is 1. Mu of 9 is 0 because I have a repeated factor and it is here, and mu of 18 is also 0. So when I add them up, I get 1 minus 1 minus 1 plus 1, and it is. It's very nice, and it's very nice theorem telling us that this always is 0, except when you took the number to be 1. You take any number, 18 or any other number, it's not 1, and I get that the sum is 0. All right, so the most useful part in applications, in our applications, our problems, will not be the formula. Because again, this formula, in order to apply it, will need lots of values to compute. So it will be just the definition. That's the most important part for us. How to compute the Mobius function in questions like this. Find the largest n for which, or less than 50, or the smallest n larger than 50, for which the Mobius function is 1 or minus 1 or 0. And I think we can close this video with the Mobius function.